Physics is the branch of science, obviously, that studies the physical world. So tell me, what's the opposite of a physical science? What's the opposite? There's two kind of branches of science, physical science and life science. Good. Okay, physical sciences include chemistry, physical science, physics, astronomy, I don't know, geology probably. Okay. Physical science is non-living things. Geology, it's rocks. I don't think they're alive. All right. So in physics, we're going to study energy and matter and the relationship between the two. So the basics of physics is how things move, why things move. Those are the types of questions we're going to be answering, right? We're going to start our whole year with talking about we're going to do conversion stuff. Then we're going to talk about how things move. That means we're going to answer questions like how fast, how far, how long did it take, right? Those are the types of questions we're going to start answering. Then we'll move into talking about why things move, right? Talking about the forces behind them and all that kind of good stuff. So physics is a lot of math. Okay, it uses math as its main language, right? Which means we use a lot of equations. All right? When we use equations, they're kind of big tools that allow us to calculate things in terms of the model of what's happening. Okay, it allows us to model our observations and then make predictions about what could happen next. So how fast is it going? How fast do we think it's going to go? All that kind of stuff. Equations allow us to do that. You guys will start using or making an equation sheet, right? Here's what my equation sheet looks like for the whole year, right? This is all the equations that we'll use for the whole year. You guys will start building your own of these as we get into our chapter, so I'll give you kind of a sheet to use for this. It's easier for me to have an equation sheet out, so I'm not having to constantly flip back into my notes, right? So I've got an equation sheet, it's got all my stuff on it, so that's what I can use. But we're going to have a lot of those. So you won't be expected to memorize equations, right? I'll give you those for you to be able to use. You have to be able to apply them. So as we think about the math that physics requires, it's really algebra, okay? Our physics is algebra based. So can you rearrange equations? Can you solve for a variable? Can you plug in numbers in multiple variables in an equation? Can you do all of those things? Yes or no? I think we should be able to answer yes. Maybe in your head you're answering these questions. If you can't do those things, maybe physics isn't for you, okay? Those are the types of things that we have to be able to do in physics. You've got to be able to solve basic equations. A lot of our questions come in the form of word problems, so you're going to have to be able to take information from word problems. So I'm just going to give you some advice here as we go through word problems. You're going to write down what you know. You've heard me say these things before, right? If I've given the velocity, I'm going to write that down in the margins, and I'm going to make a list and all that kind of stuff. Write down what I know. We're going to make a list of our margins of what we're talking about. We're going to find what equation we should be using, and we're going to plug them in, right? That's pretty much it. Find out what we're using, find out what we're solving for, plug it in. Yeah.
Did you like that, Jason?
I did. Isn't it fancy?
It's like
I can draw it. I know, it's cool. Okay. All right. When we solve for our physics problems, the things we've got to start looking at, first of all, is our answer rational? Does it make sense in context with our problem? If we're talking about a sprinter running a 100-meter dash and it tells us it took them 648 seconds to do that, is that probably rational? I would hope not, right? I think we can sprint the 100-meter dash faster than that. But you've got to start thinking about, does your answer actually make sense? Or if my answer came out to be 0.4 seconds, that's not rational either. So you've got to start thinking about, does my answer apply? Does it have the correct units? We're going to start being able to apply. If I'm solving for time, what do you think my unit's going to be? No, what's the unit? Seconds. If I'm solving for how far something went, what do you think my unit might be? Meters. Good. If I'm solving for how fast something went, that's probably going to be meters per second. Okay, so our units have to be on there as well. All right, so we got to check all these things as we solve for word problems. Let's get into measurements, okay? We use measurements to help us quantify observations. So what does the word quantify mean? To do what?
make it to a number.
Yeah, good. Put a number with it. So quantify means put a number with it. When I say, oh, that's a pretty long distance, like that doesn't mean anything, right? That long is relative to what? Okay, so when I say, oh, it's a distance of 3,246 meters, okay, that gives me a definitive quantitative measurement. So when we take measurements, you've heard me say this before, we always read what the instrument gives us, and then we estimate one more digit. We estimate one more digit. We've talked about that, and we've used that practice before. We're going to do that a little bit at the end of the week in a measurement lab, but read what the instrument gives us and estimate one more. Do we want to do one practice of what that looks like? Okay, I'm going to give you an example here real quick, okay? So let's say that I've got a ruler here. Let's say this is 14 centimeters and this is 14.5 centimeters. Right, and it keeps going, whatever. And whatever I'm measuring is this long. Okay, whatever I'm measuring happens to be that long. Okay, so as I come to measure, I'm going to read what the instrument gives us. So I know it's 14.1, 14.2, 14.3. I know it's at least 14.3 centimeters long. Would we agree with that? But is it 14.4? No, so how do I know where it falls between here? It's a guess. That's my estimate. I'm reading what the instrument gives me up to the 0.3, and then I'm estimating one more digit. So if I'm going to look between that, I think it falls about 0.37. That's what I would say. Now, this last digit is just that. It's an estimate. So it doesn't necessarily have to be exactly what I say it is. It's got to be in the ballpark, though. Okay, that's what we're going to practice later this week is you're going to be measuring things and comparing them to mine. Okay, so that's my estimate. These are my for sure digits. That's my estimated digit. Cool? All right, we evaluate our measurements using terms called accuracy and precision. Do those terms ring a bell to you? Accuracy and precision. Okay, precision means how close together our measurements are. So we want ideal groups of measurements or ideal data collections are both accurate and precise. Okay, that means they're really close together. And accuracy means how close they are to the actual number, the actual measurement. Okay? I don't want to use the word real. I want to use actual because they sound alike. Okay? So accuracy is close to the actual measurement. Trying to make a bullseye. Yeah, it's pretty close. Okay, if I'm looking at this bullseye here and I've got all of my attempts at hitting that bullseye are right there. What are my measurements? Are they accurate or are they precise or are they both? They're precise, but are they accurate? No, right? Because they're not really close to the bullseye. If my my attempts are like this, what are they? It's not really either, right? They're really not precise because they're not grouped together. I've got one accurate one that's on the bullseye, but that's not a good set of data collection. If I want them to be accurate and precise, they've got to be all around the middle there, right? That would be a data collection set that looks good. All right. So let's see, let's talk about in a real lab setting. In a real lab setting, how could I have measurements that are precise but not accurate? What would cause me to have measurements that are precise but not accurate? I want you to think about this in a lab setting. How could my measurements be precise but not accurate? Bingo. That's what I'm thinking. Okay, so let's say we've got, you're measuring the length of something, and you just, for some reason in your mind, are reading it at 62 centimeters when really it's 67, right? You're 5 off or whatever. That means your measurements might be really precise, but like they're not really close to what they're supposed to be, right? So if we read an instrument incorrectly, but we do it over and over and over again, that could lead to precision but not accuracy. Okay, so that could be one. If I have different people reading an instrument throughout an experiment, they're probably going to see it differently. Okay, they might just view things differently, right? They might be on a different level. Things just happen, right? People measure things differently, so that could lead to maybe accuracy, but not precision or whatever it might be. So as we get into these lab experiences, you want to make sure that the same people are measuring for that set of trials. That way, you have consistency throughout those sets. Okay, so do we feel okay about taking the measurements? What's the tagline for taking measurements? Read what the instrument gives you, then what? Then add another or estimate one more digit. Okay? You'll hear me say that as we get into our measurements a little bit here. All right, let's talk about the metric system. Okay, it's also called the SI system. SI stands for System International. We use the metric system so that people in other countries know what we're talking about, because no one uses the U.S. system except us, right? So no one cares how long an inch is, okay? And no one cares how much is in a pound, right? They want to know it, and so it's universal. So we use the metric system scientifically. All right. These are the base units for the metric system. Did I include this table on your... Okay, so I don't have you filling in anything. Okay, these are all the basics. So I want you to notice one of the units kind of sticks out to me as being different than typical base unit. What do you think? Kelvin measures temperature, but I think that's okay. CD is called a candela. No, that's not what I'm talking about. Yeah, Lily. Which one? Okay, moles measures amount. Yeah, those are all okay. The one thing that sticks out to me is this kilogram. Why is it not just gram? Right? Kilo is a prefix. So why is it kilograms and not grams? Okay, the reason that it's called the base unit for mass is because if we measured everything in grams, we would be dealing with thousands of grams for every measurement, because grams is a really small unit. So when they call it the base unit, they're saying that it's most commonly measured in kilograms. That's what I think the difference is. But when we talk about our measurements in conversions, grams is still where we find like the middle of that chart. Right, okay, so I'll show you that here in just a little bit. We're still going to use the prefixes off of gram, but kilogram is technically the base unit, not gram. Okay, so Celsius is common. Kelvin is just the more... those two are pretty interchangeable for us, but Kelvin is considered the official temperature because Kelvin is based off the scale that goes all the way to 0, which is called absolute 0. So 0 Kelvin is when atoms cease to move or exist. Negative 273 Celsius, right, is absolute 0. So that's why it's based off of that scale. But we use Celsius more often than we use Kelvin, honestly. But good question. All right, here's our metric system conversions. All of these are on a scale of 10. I wrote the chart how I like to use it. If you like a different chart, that's fine. But you need to understand here's where the basic units go. So meter, second, grams, liters, could also be any of the other ones. But here's how we apply that. Okay, I like to always give the larger unit the 1 and then tell how many of the smaller units are contained in that big unit. That's why you see up here mega and kilo are the larger ones. There's some ones that fit in the middle there like hecto and all that kind of stuff, but I only put in the ones that are the most commonly used. Okay, now in some classes previously I let you use that chart, but I'm not going to let you use it anymore. Okay, so this will be ones that you probably have to have memorized. Capiche? Okay. You'll start getting used to the ones that we use a lot, right? There's some on here that we just don't use that often, but you'll get good at the ones we use a lot, okay? All right. Other conversion factors here are from the U.S. system to the metric system.
Did we get this one?
No. Very few of these do we use that often. The one that we use often is either one of these. Here's what I'll suggest. When you're talking about memorizing these conversion factors, I would pick one length conversion factor and let that be it. So I would maybe memorize inches to centimeters, and then whenever I have to cross over to the metric system from the US system, I just need to work my way to inches and centimeters, right? Even if we start in miles, I'll just go miles to feet to inches to centimeters to meters to whatever. You know, it might take more steps, but I've only got to memorize one of the conversion factors. Does that make sense? So pick one, whether it's feet to meters or inches to centimeters, and memorize that one. Same with these two. These are both for like mass, so just pick one of them and memorize that one. Okay, and then you could always work your chart to get to that conversion. Okay? All right, very good. Let's do some practice here. Okay, it says Ty ran 2.433 kilometers. How many centimeters did he run? And also, how many miles did he run? So we're gonna have two different conversions here. Now, as we start our conversions, what do we always start with? What we know. Very good. 2.433 kilometers. We're gonna draw our T. Okay. If I want to go from kilometers to centimeters, what's my middleman there? Meters. I'm going to get rid of kilometers, go to meters, get rid of meters, and go to centimeters. Okay, and then I can fill in my numbers. These might be ones that you feel familiar with already, but between kilometers and meters, which is my larger unit? Kilometers, and how many meters are in a kilometer? 1,000, right? Kilo means 1,000. So there's 1,000 of the base in a kilo. And then meters is larger. How many centimeters are in a meter? 100. Good. What's centi mean? It means 100. So from there, I've canceled my units. I've gotten rid of kilometers, gotten rid of meters. I multiply across the whole top, divide by the whole bottom, and I'm going to get a lot of centimeters, right? 243,300, I think. 1, 2, 3, 4, 5. I'm going to move it 5 places, so that's a comma, not a decimal. Okay, 243,300, and I want to make sure I put my unit on the end there, centimeters. Now, does that answer seem rational? Should we have ended up with a larger number of centimeters than kilometers? Yes, very good. Okay, if we were going the other way, we should have ended up with a small fraction of a number, right? Okay, now how many miles did he run? We can start from centimeters or we can start from kilometers. I'm just going to start from kilometers. 2.433 kilometers. Some people know the conversion from kilometers to miles right away. That's fine. You can use that if you do. I think it's 1.6, but I'm not confident enough in it. I'm just going to move on. I'm going to go to meters. Then I'll go meters to feet. Then one more, I'll go feet to miles. Okay, so it takes me a little bit of an extra step if I don't know that conversion right away. Kilometers is 1 to 1,000. 1 meter, no, we went the other way. 1 foot is 0.305 meters. That's the only one I don't do the right way necessarily. The bigger one gets the 1. And then how many feet are in a mile? 5,280 feet. Okay, so I got 1.51 miles. Now, tell me, does this answer seem reasonable? Yes. Yeah? What do you know about a 5K?
It's about 3 miles.
It's about 3 miles. So I've got almost half of a 5K, so I've got almost half of 3 miles. So that works out. Okay? Questions about the conversion process. We feel comfortable with the T-chart. We just didn't remember the numbers that go in the T-chart. Is that right? Okay. Try that one on your own. How many seconds are in a leap year? How many seconds are in a leap year? What do you have to know first? You got to know how many days are in a leap year. Tell me how many days are in a regular year.
365.
365. So what happens in a leap year?
166 days.
There you go. You get one extra day. So you start with 366 days, converted all the way to seconds.
It's just February.
Okay. What does this mean? What's this slash right here? What's it mean? Per. So what does per mean?
How many meters?
It means over or divided by. Okay, so let's look at this. Now, when we set up our conversion, we have to do it like this. 1.3 meters per second. Okay, per means divided by. This is saying we're traveling 1.3 meters every 1 second. You don't need to put the 1 there, but you can if you want, but 1.3 meters every 1 second. So now we have to do a conversion for both meters to miles and seconds to hours. So we've got to do both of them, but we can do them in the same chart. So I'm going to go meters to miles first. So meters to feet to miles. Right? I'm going to do that conversion first. So we said that there is 1 foot is 0.305 meters, and 5,280 feet is in 1 mile. I'm not going to do the math yet. I'm just going to sit right there for a second. If I stopped right there, meters would be canceled, feet would be canceled. So what would my units be if I stopped right now? Miles per second. Right? If I did the math, my speed unit would be miles per second. But I don't want miles per second. I want miles per hour. So now let's think about this. If seconds is on the bottom, where does it need to be canceled? On the top. Okay, so now I'm going to take seconds, put it on the top, and I'm going to go to hours. Okay, you could go seconds to minutes, minutes to hours if you want. But we already said that there's 3,600 seconds in 1 hour. What'd you say? I didn't cancel out miles. I just stopped right there. What I'm canceling out is seconds here to here. You can do it in the same chart, but technically, yeah, it's a different conversion. So you could convert meters to miles, stop, do seconds to hours, stop, and then do the division later. But I just want to do it all in one step. Okay, so yes, it's a different conversion. But I stopped with miles. I can circle that one if you want, so you know, like, we're stopping right there. I'm rid of seconds, so now I'm in miles per hour, which is what I want. And now I can do the math all at one time. So multiply across the top, divide by the whole bottom. You'll find out this bird is moving pretty slow. I'm not even sure it's fast enough for him to fly, but divide by 0.305 do it. No. I didn't get that. Oh, okay, you're just taking a guess. I got 2.91 miles per hour. So it's moving pretty slow.
Start to fall.
Maybe. Maybe. Okay, how do we feel about that conversion with the double? Okay, you're going to have to do both of them. That's a more common conversion that we'll have to do because we might see it in kilometers per hour. We want meters per second, all that kind of stuff. Okay? All right, I want you to try this one on your own. Try this one on your own. Is that what we had? 25 meters per second?
Yes.
Okay, now I'm going to show you a shortcut for this conversion. This conversion we do a lot. A lot. And every time we do the conversion, this part of my conversion chart would look the same, right? No matter what kilometer per hour I start with, this part of my conversion is going to look the same. And this part of my conversion is the exact same as dividing by 3.6. So if you take 90 divided by 3.6, what do you get? 90 divided by 3.6, you get 25. So this, I want you to write this down as a shortcut. If I need to go from kilometers per hour, and I need to convert to meters per second, I'm going to divide by 3.6. Divide by 3.6. Okay? That's my shortcut. Now, if you don't want to memorize that, that's up to you. You can always do the conversion, right? The conversion will work, but this is helpful if you want to go a little bit faster. Okay? What do you think would be true of the conversion if I needed to go the opposite way? I would multiply by 3.6. If I needed for some reason to go from meters per second to kilometers per hour, I would multiply. Now, you need to understand this is only true for kilometers per hour or meters per second. If you change any of the units with that, it doesn't work, right? The shortcut is only for that specific conversion. And I only give it to you because we use it a lot. Okay?